Hello, welcome to this lecture on geology, topography and climate of the Lesser Antilles. Readings for this lecture are as on the note here, from the Encyclopedia of the Islands, the chapter on Antilles, Geology, the chapter on Oceanic Islands, the chapter on Volcanic Islands, climate on islands, and lastly on hurricanes and typhoons. The first three being of geology and topography, and the last two mainly about the climate side of things. Okay, so I'm going to go through this lecture and I will give you all the information that you need, and I would have expected you to have seen this lecture and gone through it when I write my questions for the exams and so on. So let's just get on with it. Alright, this lecture is on setting the geological and climatological scene for Lesser Antillean biogeography. So we want to talk about tropical islands, we want to talk about island arcs, we want to talk about the specifics of the geology of the Lesser Antilles, but also we need to take a look at the generalities of islands and their climate and their geology. So we are talking about the Caribbean Sea, and in particular we are talking about the Lesser Antilles, which on this satellite map is this chain up through here. These are the Lesser Antilles. The Greater Antilles are these bigger islands here. Okay, the Lesser Antilles here. And Trinidad is down here, and as you can see, it's not actually part of the Lesser Antillean chain. It's actually still on this continental shelf, which you can see there. Now, the reason why we're considering the Lesser Antilles by themselves is mainly because they all have a very common geological origin, and they also have a a similar climate and so on. So I want to talk about geology first of all of the Lesser Antilles, then we'll take a look at topography and what the geology means for the topography. Then we'll start talking about climate, tropical climate in general, and then specifically in the Lesser Antilles, rainfall patterns, hurricanes, and finally we'll take a look at topography and climate interactions. All right, geology. First of all, we need to give you an overall setting. Where are the Lesser Antilles with respect to the overall global geological situation? Okay, and on this diagram here, it gives you an idea of where the Lesser Antilles are. Here they are here on a tectonic plate. As you probably all know, the Earth is covered by a set of tectonic plates, which are much like broken eggs on a broken eggshell on a hard-boiled egg, for instance. And those plates are actually in motion. They're pushed around by convection currents in the mantle, in the molten part of the Earth. The Caribbean plate is actually moving to the east at about 2 centimeters a year, and it is pushing eastward, and the Atlantic plate is pushing underneath that Caribbean plate as it pushes eastward. So what I've got here, Caribbean plate pushing eastward under the Atlantic plate, that's actually wrong. It should be pushing eastward over the Atlantic plate. And on the western side of the Caribbean plate, we have another subduction zone. This zone where the one plate goes underneath the other is called a subduction zone. See if I can write that down here. Subduction zone. And a subduction zone has some very distinct geological features which lead to the formation of islands and particular island arcs. We also have a subduction zone on the western boundary of the Caribbean plate and associated volcanoes with that as well, and I'll show you that in a next slide. But I'll introduce you to a term, volcanic arc oceanic islands, and that's what the Lesser Antilles are. As you can see, they're arranged in an arc, okay? So, and they are islands which occur in the middle of the ocean. Oceanic islands basically had not very associated with any continents, and they never have been. So they tend to have a biota which is evolved independently. Right, so they're volcanic arc oceanic islands. Okay, and they form in association with a subduction zone where one plate goes underneath another plate. The Caribbean plate is actually overriding over the top of the Atlantic plate here, and they've got North American, but I think it's Atlantic plate here, because the Caribbean plate is less dense than the very dense oceanic plates. And the same reason on the western edge here. The Cocos plate is an oceanic plate, and the Nazca plate is an oceanic plate, and when it goes down underneath a lighter plate, it's the plate which gets subducted. Okay. One more point. You can see that these two, the western and eastern margins of the plate, are subduction zones. The northern and southern margins of the plate are also marked by faults, where one plate moves against another. The southern edge of the plate is marked by this fault, and on the southern boundary is the South American plate. You can see the fault runs right through the middle of Trinidad there. So north part of Trinidad is on the Caribbean plate, and south part of Trinidad is actually on the South American plate. No volcanoes along these types of faults or these plate margins, mainly because these plate margins are not subduction zones. Okay, those faults, there's no one plate going underneath the other. Instead, the plates are shifting relative to one another. And these are known as transverse faults. And they don't come with volcanoes. They do actually come with earthquakes, however. And the big earthquake in Haiti was probably associated with this transverse fault on the northern boundary of the Caribbean plate. If we look at having trouble changing slides here. If we look at the next slide, this slide shows earthquake frequency around the Caribbean and volcano occurrence. As you can see, we get volcanoes on the Lesser Antilles, on the eastern margin of the Caribbean plate, and we also get volcanoes in Central America along the western edge of the plate. The red crosses are earthquakes, and as you can see, majority of earthquakes go around the boundaries of these plates. The boundaries of the subduction zones are fairly well defined by earthquakes, volcanoes, and so on, and part of the transverse faults as well marked by earthquakes. The southern boundary of the Caribbean plate isn't really that clear when it comes to mapping out earthquake occurrence. There really does seem to be a whole mass of earthquakes in this whole region, so nobody really knows where that boundary actually lies. So, why do we get these volcanoes associated with these subduction zones? And the answer is here. If we look at this diagram here, this is a cross-section from around St. Vincent through Barbados out to the plate boundary. And as you can see, this is the oceanic plate. It's disappearing underneath the Caribbean plate here. Okay? As this plate descends under, and it's moving westward underneath the Caribbean plate, the sediments which naturally were deposited along this oceanic plate are all scraped up together, and they form this huge wedge of sediment which is also deformed and metamorphosed. Okay? And that can cause a little crest along with a slight upwarping of this. It's not very evident in this diagram, but an upwarping of this oceanic plate as it goes down. So if you look at my diagram there, if this is the oceanic plate and this is the Caribbean plate, the oceanic plate is going down underneath, and as it goes down underneath, it's quite rigid, so it bulges up as it goes down, and this bulging area also causes islands to rise above the sea, and that's how we get Barbados. The main islands of the island arc, however, are volcanic islands, and they originate from this oceanic plate and the associated sediments taken down into the mantle and subsequently melting, and the fluid which is formed from that melt from the sediments and the oceanic plate is actually lighter than the surrounding magma. And because you have this lighter liquid in the magma, it wants to try and get to the surface. So it migrates through the mantle north upwards until it hits the crust once again, and it forms these magma chambers. Okay, and these magma chambers in the crust periodically shoot magma to the surface, and as they do, they build up these islands. Okay, and because this subduction zone is along a boundary, okay, the islands will form also along a boundary just inside of it. Okay, so if this is the plate boundary here, the oceanic plate is subducting underneath the Caribbean plate. By the time the oceanic plate material, the sediments and the actual material melts, then it's much further to the west, and that's where the volcanic islands form. Okay. All right. So, what sort of islands do we get? We get volcanic islands mostly. Barbados is an exception, and I'll talk a bit about that in a minute. But the majority of the islands are volcanic arc islands. Now, there are two distinct arcs in the Lesser Antilles. There's the inner arc, or the current volcanic arc, and there's also an outer or old volcanic arc, also known as a forearc. This old arc is actually made up of extinct volcanoes, where the melting zone has moved further westwards, so that the volcanic activity has now moved further westwards. There's Montserrat there, and Martinique, and so on. So that this set of volcanoes here on this, along this part of the Lesser Antilles, these volcanoes are actually extinct. And as they become extinct, they no longer build up, so they are eroded away. Okay? But before they disappear beneath the sea, they have fringing coral reefs, and they form limestones. And that limestone builds up to form some limestone islands on top of these old volcanic islands. All the current volcanic islands also have limestone fringes, but because they're relatively recent, they've still got their volcanic rocks above the water. A lot of these old volcanic islands, their volcanic rocks are now below the water, and all you're seeing is the limestone. Okay, so two distinct types of islands in the Lesser Antilles, the current volcanic islands and the old volcanic islands, and they have very different topography. Barbados is an exception because its origin is not with volcanoes, but it's with that deformed, compressed sedimentary wedge, or accretion wedge as it's called, which is scraped up from the oceanic plate as it goes down underneath the Caribbean plate. Okay, so Barbados is not volcanic in origin, but all the other islands of the Lesser Antilles are. Right, so these islands are different, and they're mainly different in topography. These islands tend to be very steep-sided and mountainous. Well, the current volcanic in the new volcanic arc are steep-sided and mountainous. They're built up from successive eruptions of ash and lava flows, which solidify and indurate, so they're hard. And these volcanoes erupt for a while, and then finally they go dormant and then finally extinct. So there are practically every island of the Lesser Antilles does have a volcano which is either dormant or active. The active ones are on, there's one on Dominica, one on Montserrat, which are actually erupting, and there are dormant volcanoes on many of the other islands. Montserrat, Sophia is currently erupting. Just north of Grenada, there's the Kikumjeni volcano, which is also erupting, but that's not actually an island yet because it's still underneath the ocean. Some of the other notable eruptions in the past were Montpellier in Martinique. It erupted in 1902 and killed over 30,000 people in a number of eruptions over the course of a couple of months. It was so devastating because it erupted with pyroclastic flows, or nuits ardentes in the French. These pyroclastic flows are clouds of superheated gas and volcanic ash at temperatures of over 1,000 degrees Celsius, moving down the side of the mountain at thousands of kilometers an hour, hundreds of kilometers an hour. So basically nothing, if you're in the way of one, you're not going to get out of the way, you're going to die. And 30,000 people in the town of, I think it was Port-Pierre, died as a result of a pyroclastic flow in 1902 on Martinique Island. So volcanoes erupt for a while and then go extinct, and so on. So some of the islands that you see, like St. Lucia, most of the volcanoes are extinct there. All right, some pictures of volcanic islands. Thank you. Okay, here we have, this is Montserrat erupting, and this is on the south side of the island, sending down some of those pyroclastic flows and mud flows down, and you can see that it's actually building out the island, it's extending the island. And this is what happens with volcanic islands. They build themselves out. This one again is on Montserrat, and this is actually the main town of Montserrat, which the name escapes me just now. Okay, yeah, the town of Plymouth. This is the Sophia volcano up here. When it erupted, it sent pyroclastic and mud flows down through the town, and it basically buried the town. So there's not much of Plymouth left. Nobody lives there anymore. People are banned from going in there because of this active volcano, which could erupt any time and send out a pyroclastic flow and basically kill people. Not many, I don't think anybody died in Plymouth. They had enough warning, so they got out. Most of the damage was done through mud flows, or lahars as they're called. But as you can see, the island is building itself, it's getting bigger, and this is what happens with these active volcanic islands. Some other images of the more active volcanic islands. These are the pitons in St. Lucia. Okay, this is, I think, the town of Soufrière. The pitons represent old volcanic plugs, or the central part of a magma chamber of a volcano, and the rocks around it have been eroded away. So you have Petit Piton and Grand Piton. Gros Piton. This is an old caldera, it's called now, called the Grand Etang in Grenada. It's a dormant volcano. It may erupt again, we don't know. Because it's dormant and there's a crater, it's in the center of the island, that crater is filled up with water, forming what is known as a caldera. And this picture here is a picture of the forest in Dominica, and this fella here is smelling some pretty sulfurous smells in the clouds of sulfur which come out of some of the fumaroles around in Dominica. Another picture of Montserrat, the most active volcano. There's Soufrière extending its island out to the east. This used to be the international airport. It's buried under a mud flow there, and Plymouth is on this side and also buried underneath mud flows. People are restricted now to living in the north side of this island, all this area in here. All the southern part of the island is now a no-go area. You're not supposed to go there because you might get erupted on, and that'll be the end of you. All right, so those were the volcanic islands which occur in the inner arc. Now let's take a look at the volcanic islands of the outer arc, the ones which have been eroded away. Oh, actually no, strike that. We're actually going to be looking at Barbados. This is the origin of Barbados. Okay, again, this upwarped sediment compressed and made into a wedge which sticks above the ocean. And this is a cross-section view, so this is the surface of the ocean here, and here's the section through Barbados. You can see the deep sea tertiary sands and limestones which have been metamorphosed. These wiggly lines are supposed to represent the bedding which has been deformed and warped as the plates, the sediment was crushed as it got scraped underneath the Caribbean plate. And on top of this basement rock you get limestone. So on the eastern edge of the island you're actually going to get these sands and limestones exposed, but the majority of the island is formed of a quaternary reef cap of limestones which increase in altitude, showing how the island has been lifted above the sea over time. First of all, this part of the island would have been exposed and this would have been the reef. Then the island got lifted up and this became the coast, and that was the reef. And then it got lifted up again, this became the coast and this was the reef, and so on until the modern day. And we've got modern day reefs in Barbados around the fringe of the island now. The other islands, the old Ark Islands, as I said, have a similar sort of origin. The difference is that instead of deep sea tertiary sands and limestones underneath, they have a volcanic origin, and then they would have the quaternary reef cap on top of volcanic stuff, not the tertiary sands and limestones. These are some pictures of limestone islands. As you can see, they're largely flat. I think this is in the Bahamas. Okay, so largely flat with lots of terraces. Okay, and they're built by coral reefs offshore, building up the limestone. Right, now the islands of the Lesser Antilles haven't always been the same way. They have increased in size with volcanic activity, decreased in size with erosion. They've joined up, they've split apart. The reasons for these changes in size are not only erosion, but also volcanic activity, increasing things, but also a major driver in changing sizes of islands are changes in sea level. During the last ice ages, the sea level was much lower as a lot of the water in the oceans was locked up in those ice caps at the poles. Okay, as the ice ages ended, the sea levels rose. With the lower sea level, you can imagine the islands of the Lesser Antilles would have been bigger. Okay, and some of those islands would be so big they would actually coalesce, they would join up. But with the return of the interglacials, sea level rises, and those islands would have shrunk in size, and islands which were formerly joined up are now split apart. So if we can see that on more of a close-up on the Google satellite image. Here's the continental shelf here. You can see Trinidad is fully on the continental shelf, and also Tobago. So during the last ice age, Trinidad and Tobago would have been part of the continent of South America. Lesser Antillean islands, however, are more or less separate. And you can also see that some of these islands, like Grenada, the Grenadines and St. Vincent, they may actually have been linked together on this ridge. Now they're just peaks showing above the water, but this ridge may have been more continuous when the sea level was lower. Okay, and also these islands would have been larger, okay, as skirts of these islands would have been exposed as the sea level being lower. Now, why do we care about all of these different types of changes in size and joining together and splitting apart? It's because they have very important implications for the biogeography of the Lesser Antilles. Species could have exchanged between islands when they were joined together. Maybe Grenada was actually linked up to the continental shelf, and it would have taken a continental biota at that time. And when it split apart, it went its own way once again. Tobago has got more of a continental flora than any of the other smaller Lesser Antillean islands, but less so than, say, Trinidad, which was probably joined onto the mainland longer. Okay, so we need to understand how these islands have increased in size, decreased in size over time, so that we can understand the biota that we get, the ecology that we get on these different islands. I'm going to take a break there and then come back and take a look at some climate